I want to give you one more example of playing this game of curve arithmetic, so you can get some more practice and learn some new strategies to crush your opponents with no mercy. This time the example will be in 2 dimensions, so it will be a little easier for me to draw. So I'm giving us a vector field f. Again, I'm not saying what f is explicitly, it's just some abstract vector field. And it's defined on R2 minus 3 different points, P, Q, and R. Also, like before, we're told that the curl is 0. We're also told the values of the line integrals of f over 3 curves A, B, and C. And we're supposed to use this information to evaluate the line integral over D. So it looks like we have 3 curves circling each point, P, Q, and R. And then the curve we actually care about is this green curve with a loop-de-loop. So before I make my first move, let me just remind you of the general strategy here. Because we're told that the curl of the vector field is 0, we know that on simply connected domains, the vector field is conservative. We want to use this to our advantage, in particular by finding closed loops in simply connected domains and using this fact to ensure that the line integral over those loops is 0. The other overarching fact here is that the whole domain R2 minus these 3 points, this is not simply connected. For example, you could pick any of the 3 curves A, B, and C and use those to witness the failure of contractibility of curves. So the point here is that we have to pick our own smaller simply connected domains along with making our own loops to somehow win. Now the first thing I'm going to do isn't strictly necessary, but I just want to show you so we can get warmed up and get an idea for the maneuvers that we'll be making. I'm going to focus on this loop-de-loop here. It's a little weird and it makes me uncomfortable, so I'm wondering if I can get rid of it somehow. And we can. Here's how. Let me call the loop-de-loop D0. I'll color that in purple. And then I'll rename the rest of the green curve, the part without the loop-de-loop, D1. The point here is that D is D0 plus D1. Here's our curve arithmetic coming into play. Now, I claim that the integral of f over D0, just the loop-de-loop, is 0. Indeed, let me show you a simply connected domain containing the loop. I'll color it in purple here. F is defined on this domain because it doesn't contain any of the 3 points. It's simply connected because it's just a disk-looking thing. And so, since the curl of f is 0, f is conservative on this little purple domain. Therefore, we can conclude that the vector line integral of f over this loop-de-loop is 0. And what's the point there? Well, the actual integral we care about is over d, but d is d0 plus d1, so the integrals break over this sum, and we just showed that the first one is 0. So we've simplified the picture with this maneuver. It suffices to consider just the integral over d1. Now let's think about what to do. Again, we care about the integral over d1, and we only know stuff about a, b, and c. Somehow we're going to have to introduce curves to relate d1 to these 3 curves. Now it might be tempting to just draw curves connecting all of them, but I claim that we don't have to worry about b. I'm just going to completely ignore it for this entire solution. It turns out that this was extraneous information that we don't need at all. It's there to throw you off. Now, why is that the case? Roughly, it's because the curve that we care about only encircles two of the bad points, and it's somehow separated from Q. But I think you'll see why B doesn't matter when we go through this process carefully. So what I'm going to do is just draw three lines, L1, L2, and L3. They connect D to these two curves, and they give some natural divisions of all the other curves. So I'm going to relabel some stuff again. For example, the half of D1 to the right of the red curves, I'm going to call D1 plus, and then I'll call the left half D1 minus. So this means D1 is D1 plus plus D1 minus. It's a mouthful. And then I'll do the same with A and C. The respective halves on the right of the red curves will be given a plus, and then on the left I'll give those a minus. Once we do that, I can identify two different loops that I can place in simply connected domains. One of them is this one in green right here. Let me call this loop L. And using curve arithmetic, we can write down exactly what L is. I follow L1, then I follow A plus, then I follow L2, then I follow C plus, but in the opposite direction of its orientation. So it'll give me a minus C plus, and then I follow L3, and then again I follow D1 plus, but in the opposite direction of its orientation. So I get a minus D1 plus. And that's the expression for L. Next, let me show you a simply connected domain which contains this curve. I can just color in a blob roughly to the right of the red stuff that avoids the holes, something like this. F is defined on this domain because it does not contain the holes. It's simply connected, and it contains this loop L. So by the same argument as before, the curl of F is 0, the domain is simply connected, so F is conservative on this blob. L is a closed loop in the blob, so therefore the line integral of F over L is 0. Now let me do the same thing with the left half of this 8. We can draw a loop like this. I'll color it in this bluish purple color. I can't tell exactly what it is. If you have strong opinions about the color, you can let me know in the comments. And I'll call that K. Again, we can do this curve arithmetic stuff to write down exactly what K is. We follow L1, and then A minus in the opposite direction of its orientation, so I get a negative A minus. Then I follow L2, then I follow C minus, then I follow L3, and finally I follow D1 minus. And again, by a similar argument as before, here's a domain which is simply connected that contains K. F is defined on it because it avoids the holes. So blah, 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 blah. F is conservative because the curl is 0 and the domain is simply connected. So therefore, the integral of F over K is 0. Okay, so we've found these ridiculous loops, and we've argued that the integral of F over each of these loops is 0, but what good does this do us? Remember that our goal is to learn about something over D, or rather, after our initial reduction, D1. And D1 I can write like D1 plus D1 minus. So here's what we need to do. Look at the expressions for L and K. What kind of arithmetic operations could we do here to generate an expression that looks like D1 plus plus d1 minus. Well, L has a negative d1 plus, K has a d1 minus. So what if we consider the expression K minus L? Let's write this out. K minus L is this mess minus this mess. And let's mix and match some terms. We have a d1 minus negative d1 plus, so that's a d1 minus plus d1 plus, that's d1. Similarly, we have a negative a minus and a negative a plus. Those join together to give us negative a. And then the c plus and c minus join together to give us a c. Finally, all of these L's cancel out. L1, L2, and L3, they all go away. So K minus L, in terms of curve arithmetic, is D1 minus A plus C. And so we're in the home stretch. This means that if we integrate f over K minus L, well, this is the integral over D1 minus A plus C. And then I can split this integral up over those three pieces. I get the integral over d1 minus the integral over a plus the integral over c. But on the other hand, integrating over k minus l is the same thing as integrating over k minus the integral over l. But earlier we showed that both of those are 0, so this expression equals 0. So now we have a simple equation involving the integral over d prime. And we can just do some algebra and solve for it. Moving the a and c integral to the other side of the equation tells us that the integral over d prime is the integral over a minus the integral over c. And in the statement of the problem, we're told that the integral over a is 3, and the integral over c is negative 2. So we get 3 minus negative 2, which is 5. That's the integral over d1, and then initially we showed that the integral over d1 is the same as the integral over d. And there we go. Checkmate, or something, whatever you want to say, we've won the game.